Nuclear chemistry. Okay. First thing we need to do is kind of review a couple of the concepts from isotopes because they directly apply here. So if I have two different isotopes, lithium-6 and lithium-7, they have a certain subatomic particle that's the same within both of them, and actually they have two because we don't see that there's a charge either. So if they are both named lithium, then they both have protons. It's the same subatomic particle. Now it doesn't say there's a charge. You could also put electrons because they have the same electrons. What do they have different? Number of neutrons. Okay, we can tell because they have different masses here. You'll apply that information to fill in this table. Now these symbols here are very crucial. You need to remember that whenever we have a name, dash a number, that number is our mass. Or when we have it set up like this, where there's a number on top and a number on bottom, the number on top is also our mass. The number on bottom is our atomic number or our number of protons. Same thing. You're going to use that to go look at your periodic table, figure out what element that is. Okay, now that's just some basic review. You need to fill these in and answer those questions. Now, reading through these notes, we find that there's such a thing as radioactivity. Radioactivity or radioactive decay is when we have our elements are slowly decaying over time, slowly breaking down. And where that breakdown occurs is in the nucleus. That's why we call it nuclear chemistry. We're only considering the nucleus. Okay, the only things that are in the nucleus are protons and neutrons. So for nuclear chemistry, we're just looking at the nucleus. And radioactivity is when we break down and we start producing particles. Now these particles are tiny. They're things that fit inside of a nucleus. Now there are a lot of really bad things can happen from this radioactivity. A lot of good things, we can get a lot of good energy from it. So our nuclear reactors are crazy, crazy productive for a tiny bit of radioactivity. But it can also be a bad thing for us if we're directly exposed to it. Okay, so we have Madame Curie and her family were the first people who discovered radioactivity. And unfortunately, in discovering radioactivity, that means that they held pieces of uranium in their hand while they were working through their notebooks and such. In fact, Madame Curie, she's the first female to ever win the Nobel Prize. She won it for chemistry. Her notebooks are still so radioactive that they're held in like a bomb shelter type situation. You have to go put on full nuclear attire to go look at her notebooks because she had a piece of uranium in one hand and her pen in the other one writing it down. Mostly radium. Madame Curie and her whole family discovered radium. There's also curium up there for her as well. Okay, so her husband, and then her daughter followed their work. Unfortunately, they all died from tumors. Now why? Well, because radioactivity causes cancer. Now why is that? Well, radioactivity is releasing these tiny nucleotides, things that go fit inside of a nucleus. They get blasted out and hit things. Remember your DNA, everything is made of atoms, so your DNA is also made of atoms. Remember, atoms are a lot smaller than DNA because millions of atoms make up your DNA. Inside of each of those atoms is our nucleus, teeny, teeny, tiny. Remember, football field is your atom. Your nucleus would be a pea on the 50-yard line. So try and think of the scale of what would be inside a nucleus versus your DNA. That would make your DNA the size of the world compared to that football field. So one of those nucleotides hitting one of your atoms in your DNA is kind of like shooting a bullet through your DNA. It's going to cause some serious damage. And the problem from radioactivity is when it causes damage to the replicating part of your DNA. What a tumor is, it's cells that have stopped doing their job and won't die. Okay, so remember back in biology you learned about mitosis, cells splitting, cells splitting, cells splitting. If you destroy their DNA, all they keep doing is splitting and splitting and splitting and splitting and splitting and splitting and splitting, and they don't die, and they keep going and keep going and keep going until you have this accumulating mass of cells that are doing nothing productive for you. And in fact, they start pushing on your other organs or damaging your other organs, right? Your organs inside you are very, very weak, very tender whenever it comes to a giant globe of cells, each pushing against it. So you can imagine a tumor in your brain. You now have this mass of cells that aren't doing anything, shoving your brain outwards. Okay, so cancer is this production of these cells that aren't doing anything. And they're caused from this radioactivity. Now, we can use this radioactivity to cause problems, but we also nowadays are able to use radioactivity to try and solve problems. One of the main ways we have to fight cancer is radiation. Now, the way we do that is we need to kill those cells. Okay, we have 2 plans to kill cancer right now. Well, 3. Chemotherapy is we make a chemical that will actually try and kill those cells, make them die and stop replicating. That's chemotherapy. Problems with chemotherapy is sometimes that chemical also kills good cells. Okay, that's why people on chemotherapy start losing their hair. They get really sick. It's really well, we're gonna try and kill off the cancer cells, and hopefully we don't kill you in the process. That's chemotherapy. Okay. The other way we do it is let's go try and cut out the tumor. Let's literally cut you open and try and scoop out all of those cells that won't stop replicating. Problem is, if we even leave one of those cells, we won't know immediately we left one of those bad cells. A few months later, a year later, or 2 years later, we go do another CAT scan and we see, crap, there's another tumor. Okay, one of those cells stayed there and kept replicating, and the same problem happened. Option 3 is radiation. We use one of the things that causes cancer against cancer. So what radiation is we aim these beams of particles. Think of it like a laser, like a lightsaber, okay? So if I have a tumor right in the middle of my stomach, I can't aim a big laser at the middle of my stomach. Yeah, it'll kill the tumor and kill everything else all the way through, like putting a lightsaber straight through me. So instead, what this genius idea is, if I have a tumor right in the middle and I want to kill it using this radioactivity, using these lasers, I'm going to set up 100 different lasers from 100 different angles around me. And each of these lasers are going to be teeny, teeny, tiny, just a few atoms wide. So each laser will cause a tiny bit of damage going through me, but not much, each individual laser. But where all of those 100 lasers are all aimed to perfectly overlap, where all 100 lasers overlap, that'll be entirely obliterated. So if we scientifically and mathematically perfectly align all of these little tiny lasers into one spot, meaning where that tumor is, we can obliterate something on the inside of you without destroying everything on the outside of you. Okay, so we've been trying to use this radioactivity, so even though it causes problems, we can also use it for positives. So there's positives and negatives to everything. I'm going to talk about nuclear energy later on in this week as well. So that's kind of my introduction to what exactly is nuclear chemistry, with the good, the bad, the ugly. Now, on to our kind of like vocab here. We have different kinds of decay: alpha, beta, gamma. You've probably heard of those. Okay, then we have neutron decay, positron decay, and proton decay. So a nuclear transmutation is when a nuclei is bombarded with nucleons or other nuclei to produce atoms of a different element. So this is how all of those UUUs, how we produce these new atoms, all the man-made ones on my periodic table, they look hollow. All of those were man-made using this nuclear transmutation, slamming 2 atoms against each other at millions of miles per hour to where their nuclei actually combine to make a new number of protons. A new number of protons is a new atom. Now, the ones that are still labeled UUU haven't lasted long enough to get a name. They immediately break apart again. They go through nuclear fission. Okay, so fission, a fissure is something that's breaking apart. You can have a fissure in your tooth, a fissure in the bottom of the ocean. A fissure is anything that's breaking apart. So nuclear fission is when it breaks apart. Nuclear fusion is when you fuse something together. So we're fusing 2 things together. Now, balancing out these nuclear equations is just a matter of adding and subtracting. All of my numbers on top and all of my numbers on bottom need to match because of my law of conservation of mass, or my law of conservation of matter. Matter cannot be created nor destroyed. These numbers represent numbers of protons and neutrons. We can't just create and destroy numbers of protons and neutrons. So all the numbers on top And all the numbers on bottom, on both sides, need to add up to the same. Now, our coefficients applied these numbers as well. So on the left side, I have a total mass of 236. 235 plus 1, 236. So on the right side, I need 236. What do I have so far? Well, I have 236 as my goal, minus 90, because I have 90 here, minus 3. Notice I have 3 of these. So how many do I have left? What is my missing number for this top number? 143 is the missing number. Therefore, I put 143 for the mass. Now my numbers on bottom must also match up. So I have 92 plus 0, so I have 92 total on this side. My other side needs to add up to 92, so the goal is 92. Minus 38 from here. Minus 0 from here. 3 times 0, it's still 0. So what do I have left over? 54. So I put that for my number of protons. And then I look at my periodic table to figure out what element this is. What element is 54? Xenon. X. E. So this uranium, I'm sure you all have heard of uranium and the fact it's radioactive. This is why. Okay? It goes through decay, it produces 3 neutrons here, and it breaks apart nuclear fission. Okay? It breaks apart into a strontium and a xenon. Now, our different kinds of decays change our number of mass and our number of protons in different ways. So alpha decay is this right here. This little helium 4/2. We call it helium because 2 protons is in fact helium. Now what happens when we go through alpha decay, when we lose one of these? Well, I've lost 4 from my mass, and I lose 2 from my number of protons, right? I've lost one of these, so 4 mass and 2 protons. A always means mass, Z always means protons. Write that on top if you need to. The A is the mass, the Z is the proton. So change in mass, change in protons. Beta decay is this little symbol here. Notice how I have a -1 in that proton position. Which actually means when I look at the number of protons, okay, for that element, it's gained 1. Notice that this was 90, and now I put 91, because 91 plus a -1 is, in fact, 90. For electron capture, well, this is capture. Instead of decay, something comes into the equation. It's on the reactant side. This creates a -1 effect to the number of protons. And then lastly, positron decay. It's decay again, so it's on the product side. This creates a -1 effect to the number of protons. For each one of these, you'll do the balancing equation we did before, and then you'll label if it's alpha or beta decay. So you're going to just say, like on this one, notice how we produced one of these, so that would be beta decay. And you identify what's produced. Now let's look at a decay series. Below is the decay series for uranium-238 nucleus, showing all the steps of decay that occur before it finally reaches a stable state. Fill in the blanks of either the type of decay that occurs to get from one step to another, or the name of the isotope produced at a certain step. Let's look at what we have so far. I start with uranium-238, and it goes through alpha decay and produces thallium-234. Well, how do I know that? Well, alpha decay creates a -4 in the mass and a -2 in the number of protons. So uranium If it loses 4 from its mass, it becomes 234. And if it loses 2 from its protons, well, look at your periodic table. 2 fewer protons is now thallium. Okay. So now I take this thallium-234 and it goes through beta decay. Beta decay means it actually gains a proton. So going from thallium through beta decay, I gain a proton. Nothing happened to the mass here. Gain a proton, and I come polonium. Then this goes through beta decay. Beta decay means it gains another proton. Now I'm to uranium-234. I'm back up to uranium, but I'm at a different isotope of uranium, different mass. If I go through alpha decay would mean I lose 4 from my mass. So now I'm at 230. And I lose 2 from my protons. So I'm back down to thallium. Now this time I was given the starting and the ending, and I need to figure out what kind of decay it is. From thallium to radium, my mass here looks to change by 2, or by 4. Started with 230 and lost 4. Well, only one thing does a mass loss of 4, so this must be alpha decay. You'll continue through here, either identifying what kind of decay is based off of the change you see, or identifying what is produced based off that decay. Then the last thing you have for homework is just a different version of writing this out. So instead of doing boxes like this, you're going to do something very similar. Start with U-238, go through alpha decay. Take that, go through beta decay. Take that, go through beta decay again. Show what happens each step. I just told you which kind of decay to have it go through each time. Show what happens. For page 113, you're going to look at each one of these, and you're going to complete the formula. Make sure that the numbers on top all add up to the same. The numbers on bottom all add up to the same on both sides. The only addition to these problems is you need to identify if it's fission or fusion. Fission or fusion. Remember, fission is like getting a fissure. It separates, it breaks apart. Fusion is when we fuse things together, so we're forming something new. So this first one would be fission, because one thing is becoming 2. Okay. And then let's go down to number 6. I have 2 things coming together to be 1, so that would be fusion. Now, looking at 9 through 17, a couple of hints. Where are the most radioactive elements? Well, look at the periodic table and see where the radioactive elements you've heard of before, uranium, polonium, things like that. Where do they lie? They're all in the same general area. How does nuclear radiation differ from a chemical reaction? Specifically, think about subatomic particles involved in each. What's being exchanged in a chemical reaction versus what's happening in these subatomic nuclear reactions. Distinguish between alpha and beta radiation on the basis of mass and charge. Look back to page 112. Look at that table. For a lot of these problems, throughout the rest of this, make sure you look for the missing number. There should always be a mass number and a number of protons. Okay, that's how you finish each of these problems. Okay, you can always find the number of protons based off of the element. Then to find the mass number, we are going to use math. So in this case, if I have the E-1 on the bottom, I go look at what kind of decay that is, put that mass on top, and then fill in the missing mass based off of what would add up to 210. Do the same thing in these. Fill out these formulas. Fill out these formulas. Always go through and identify if there's a missing number anywhere. At the very bottom, how are mass number and atomic number of the nucleus affected by the loss of the following? So if I have alpha decay, so I lose an alpha particle, what happens to the total mass and then atomic number? Go look back again to that table on page 112. For page 114, once again, we identify the missing numbers. So on the bottom here, the bottom there. Okay. You look at the periodic table to find out what each one is. So for iodine, it's 53. I'm going to zoom in. And for xenon, it is 54. Now it says to write out the nuclear equation. So we have iodine becoming this xenon. We need to look at what kind of decay that is and compare that to the table from page 112. So if I look at my mass stays the same. So it's definitely not alpha decay. And if I look at my number of protons, my protons go from 53 to 54. Okay, so I have an addition of a proton. I go look and see what kind of decay that is, and I look and see that to be a beta decay. When I gain one proton and no change in mass, you write out the beta decay formula based off of the table on page 112. Okay, you have your reactant here, your product here, and make sure you add in the beta decay, the beta particle. Once again, fill in each of these. Always identify the missing number. Fill in each of these. All the way to the bottom. Write the balanced nuclear equation for beta decay, balanced for alpha decay. Balanced for this one, take radium-226 and have it go through beta, alpha, and gamma. Now I haven't talked about gamma decay. In the page 111 in the notes, it talks about what gamma is, but we haven't really looked at how you draw it. A gamma particle, that's a symbol for gamma. It looks like a Y. And the numbers for it are 0 and 0. Okay. What is dangerous about gamma decay, and if you've ever read the Hulk stories or ever seen the movies, supposedly it's gamma radiation that makes the Hulk. Okay, and it is true that gamma radiation is very dangerous. Gamma radiation is the smallest wavelength. If you think back to electromagnetic radiation, that really, really, really tiny wavelength, it goes through and it is smaller than a proton or a neutron. So this tiny wave, when it goes through your nucleus, can knock out a proton or knock out a neutron, which would of course cause the rest of the different types of decay. That's why gamma decay is a problem. Even though it itself doesn't have any mass and it's not have a proton in it, but because it's such a tiny little wave, it can actually cause the other decays. So when you write it into the equation, it doesn't really have an overall effect on the equation. But for this problem, I still want you to write it in. And all of these are called decays, so all of these should be on your product side. So take this, put all those on your product side, and see what's left over. How are the following mass number and atomic number of the nucleus affected? Once again, look back at page 112. And then for this bonus question, this extra credit will be added on to your packet quiz from today, and the one from tomorrow over this information will be combined together, and this extra credit will go on that. So if you didn't do well on today's packet quiz over 111 and 112, I'd make really sure you do this, as this will be your last daily grade of the semester.